I think few people have drive today, right? Okay, so good morning all. Let me start off with presenting the screen and we'll have a quick recap of what we discussed in the previous class. Right, so we have started off with the gradient descent rule, and we in the previous class we saw the stochastic approximation to gradient descent. Right, how is it different from the standard gradient descent, and what is the difference here in the stochastic approximation? Right, so that if you make it full screen, yeah. So we first saw the difficulty that we see when we apply the standard gradient descent, right? The difficulty of converging to a local minima, right? That it can be a little bit slow, and when we have multiple local minima, it can be not guaranteed that the procedure will find the global minima at the end, right? So these were the two main difficulties that we face when we apply the standard gradient descent. So how can we come upon to solve or somehow, you know, resolve these difficulties and bring out a better solution? So there we saw how we can make use of stochastic gradient descent. Right. So one common variation is intended to elevate the difficulties is called incremental gradient descent. Right. Or in other words, stochastic gradient descent. Right, so we saw the idea behind was to approximate the gradient descent search by updating weights incrementally. Right, we update the weight incrementally and following the calculation of error using this formula. Right, for each individual example, we calculate the error. So I hope you remember in the previous class we discussed like how it is different from the standard gradient descent. The standard gradient descent take the summation, the error of considering all the training examples, whereas in the stochastic gradient descent we consider each and every example, we calculate the error, right, for each and every example, and then we solve it. So that is one difference that we saw. Right, we saw a few formulas which can be modified in the gradient descent to make it a stochastic gradient descent. Right, hope you remember the algorithm, gradient descent algorithm. This algorithm. So this formula over here, that is equation T 4.1 and T 4.2. These two has to be changed in order to make this standard gradient descent algorithm a stochastic gradient descent. So this equation T 4.2 is completely removed, and T 4.1 is replaced with another formula, that is this. Right? So T 4.1 will be replaced with this formula in order to make that standard gradient descent algorithm a stochastic gradient descent. Right, and the formula to compute the error, as I mentioned, there is, if you can notice, there is no summation here, right? There is no summation symbol because we are not considering all the training example here. We are calculating the error for each individual training example, right? So there is no summation. We are considering only that particular one example and then compute the error, and then finally we will see all the other errors in order to come to a standard, gradient descent. So these are the differences, as I mentioned, that error is summed upon all the training examples, whereas in the stochastic gradient descent, the weights are updated on examining each training example, right? So we saw a case wherein we have multiple local minimum with respect to the error. Then stochastic gradient descent can sometimes avoid falling into local minimum, right? The reason is because it uses various gradient of error vector rather than gradient error vector to guide its search, right? For each training example, as you can see here, it is error ED, right? So this is for the error of each training example, whereas this is the error for the overall training example, all the training examples. So in short, if we want to sum upon and give up small remarks, on these different algorithms, then the key differences end up having that the perceptron training rule, right? The difference here is between the perceptron training rule and the delta training rule. These are the two different algorithms, right, that we saw. So the perceptron training rule updates weight based on the error in the threshold perceptron output. Right? This is very important. Please make a note of it. That is, the in the perceptron training rule, the weights are updated based upon the error in the threshold. Right? That is nothing but the change in the weightage that we do. So hope you remember the formula that we have computed for that. So delta W is equal to delta W plus no, delta vector W is equal to delta W plus the change in the weight, right, or the modification in the weight. So error in the threshold perceptron output, but in the delta rule, updates weight based on the error in the unthresholded linear combination, right? So this is one difference with respect to the perceptron rule algorithm and the delta rule algorithm. Another difference is that the perceptron training rule converges to a finite number of iterations to a hypothesis, right? So the number of iterations are finite here with respect to the hypothesis that are perfectly classified or correctly classified, right? But provided that the training examples are linearly separable. So in the perceptron training rule, as we have discussed earlier, the training examples need to be linearly separable, right? Hope you remember the diagram, the two axes that we have drawn, and we saw an example of positive training examples and some negative training examples divided by a line, right? It can be easily separable by a straight line. But there will be few examples which are not linearly separable, which are known as non-linear separable training examples. So in that case, the delta rule converges the asymptomatic towards the minimum error hypothesis, possibly required to unbounded time, but converges regardless whether the training data are linear or not. Right? Whether the data is linearly separable or not separable, the delta rule will still converge to a asymptomatically towards the minimum error hypothesis. So that is the difference between the perceptron rule and the delta rule. Right. So these rules, if we have carefully noticed, these rules are basically only on a single layer, network, just a single layered network, a single perceptron. But what if we have a multiple layered network with multiple, you know, perceptrons, and then we can try to converge these difficulties that we are facing or the problems that we have with respect to the perceptron training rule as well as the delta training rule, and ultimately converges to the minimum error using a multiple network, right? So that will give us more flexibility. Flexibility how? Flexibility in terms of it can be easily applied on the training examples which are not linearly separable, or else which are very difficult, even if they are not linearly separable, they are very difficult to be separated. So in that case, a multi-layered network will be helpful and will give you a better result compared to these two algorithms. So in order to do that, we have to first understand what is this multi-layered network, right, and the backpropagation algorithm. So currently we'll keep this backpropagation algorithm aside. We'll first discuss what is this multi-layer network, right? So basically the kind of multi-layer network learned by this particular algorithm, which is the most important algorithm in artificial neural network, the backpropagation algorithm, that it is capable of expressing a rich variety, right? A rich variety of non-linear decision surface. As I've just mentioned, that there will be few examples which cannot be linearly separable, or there will be few non-linear examples itself that they are not easily separable. So they are quite, uh, difficult or very sophisticated examples wherein differentiating those training examples becomes difficult, right? So multi-layer network will allow us to do that by expressing a rich variety of non-linear decision surface. Now, what is this non-linear decision surface? We'll shortly see. So just to give you an example, let's say we have a typical multi-layer network and a decision surface where the speech recognition task involves distinguishing among 10 possible vowels. right? So let's say we have a problem to recognize the speech of vowels, right? Distinguishing the vowels, that distinguishing among 10 possible vowels, right? So let's say we have spoken context, a context uh, of h dash d or h underscore d, whatever, and this underscore or this hyphen can be replaced with any other character, that is any other vowel, then how it can be pronounced, right? So it's kind of a speech recognition with respect to the context of, let's say for example, this h underscore or h hyphen d, that is, the examples can be hid or had, or it can be head, or it can be who'd, or furthermore examples, right? So we just have this task of recognizing the speech of pronunciation of different uh, word, let's say for example here h underscore d, right, in context of vowels, right? That is the 10 possible vowels. Now, what are these 10 possible vowels and what are the different contexts we will see here? Right. So, this is a normal diagram, a normal representation of the multi-layered network here, right, which is a feed-forward network, if you can see, right. The arrow denotes that this is the input layer, right, this is the input, this is the hidden layer, and this is the output layer, right. So, and input is given from here, and this is where we get the output. So it's a feed forward network. So we have this multi-layered network, right? And we also have a decision surface, which you can clearly see. We have few dots, a few symbols, few characters, kind of triangle, square, circle, some arrows, right? Plus symbol, uh, cross symbol. So we have different combinations of different words here. So our job is to differentiate this. We need to define or we need to separate these training examples, right? But as you can clearly see, they are not linearly separable. Definitely not, right? So there cannot be a single line which can be drawn which separates these training examples. Now, training examples. What are these training examples? For example, let's say these square. Here is we have legends here, as you can see. Square denotes the word head, right? The triangle structure denotes head, plus denotes hod, cross symbol denotes had, and rhombus kind of structure denotes that hod. Inverse triangle denotes herd, circle denotes heap, left pointing arrow denotes hood, and right pointing arrow denotes hood, and upper pointing arrows denote hood. Right. So as you can see, there is very slight uh, change in the pronunciation or very slight difference in the pronunciation, but our job is to recognize that the difference in the pronunciation. So these are the different vowels which has been used in this particular context. Now, what is this multi-layer network here? We will understand each and every aspect here, right? So uh, this particular diagram is just the decision region of this multi-layered feed-forward network. Now, what are these things? We will look one by one. Now, the network here shows that here it was trained to recognize one of the 10 vowel sounds, right? One of the 10 vowel sounds occurring in the context of HD, right? So, as I mentioned, it can be had, hid, hood, hod, anything, right? So, the network input is actually a two parameter, that is F1 and F2. From the diagram, if I have to show, right, we have two inputs, that is F1 and F2, which are the two network input parameters, right, which are used basically obtained from the spectral analysis of the sound, right. Just assume that these are the two different inputs which we have got after some analysis, which is actually a spectral analysis of the sound. And these two inputs, which are the two parameters, we are giving these two inputs as the input for our multi-layer network. Right. So the 10 network output corresponds to the 10 possible vowel sounds. Now, what are these 10 network outputs? Let's say we have this 1, 2, so on till up till 9 and 10. So we have 10 different, output, network output, representing 10 different pronunciation of that word, right? So 10 possible vowel sounds. So the output notes represent the vowel sounds, possible vowel sounds. The network prediction here is the output whose value is the highest, right? So whatever the network prediction will be doing, the value of a particular output unit here, whichever output unit's value is highest, that is of course is preferred, uh, and can be likely the rightly pronounced word, right? So the network prediction is the output whose value is the highest. Now, what you see here, this plot, as I mentioned, it is highly non-linearly separable representation. So it's a plot which illustrates highly non-linear decision surface represented by learned network. Right. So this is a highly non-linear decision surface. Now, as I mentioned, the points shows on the plot are test example distinct from examples used to train the network. Right. So points which are shown on the plot are test example which are distinct or different from the examples which we have used for the training purpose. So these are the uh, new input, new training example given to the model. Right. So hope you got the difference here now. As you can see, this is the learned model. As I mentioned, it is the learned model, and it is somewhat uh, successful. You can say that to separate the similar, uh, pronounced word. You can say so. It is somewhat able to differentiate among these by drawing the lines, you would say, or a structure or a region, right? A decision region. So that is beauty of the multi-layered network. Now, in order to understand it more, let us go a little more into depth and how is it possible for a system to do that, right? So a differentiable threshold unit, right? Now, in the most of the previous example which you have seen, for example, the perceptron rule or the delta rule, right? The linear unit or the perceptron unit and these things. So the previous example what we have seen, they all have some limitations, right? For example, the linear unit. The linear unit is restricted and it can only produce a result when we have linearly separable training examples, right? Which we have discussed in the previous lectures. So the problem with the linear unit is that it produces only the linear function, only the straight function, the straightforward training examples. And the problem with the perceptron unit is that it has the discontinuous threshold, right? It has the discontinuous threshold, which makes the segregation of this the input that we have little difficult. So in that case, we are looking for a network or we are looking for a model which can provide us not just linear but non-linear representation, right? As well as a not discontinuous threshold but a differentiable threshold, right? It can be a continuous or a differentiable threshold function. So according to that, according to our need. What is our need? The need is we need a unit. We need a unit whose output is non-linear function of its input, but whose output is also differentiable function of its input. So these are the two important terms here. It, the output is a whose output is a non-linear function of its input, and also its output is differentiable function of its input. So these this is the unit that we are targeting. We need something like that. So one solution here is the sigmoid unit, right? The sigmoid unit. What is this unit? As you can see here, this is the diagram of the sigmoid threshold unit. Now, what is this sigmoid function or a sigmoid unit, which can be a potential solution for what we are looking for as a non-linear function and a differentiable threshold unit, right? So this sigmoid function is a unit which is similar like a perceptor, as you can clearly make it from the diagram, right? It is almost similar to the perceptor, right? But it is based on the smooth differentiable threshold, right? It is based on a smooth differentiable threshold. So unlike the perceptron, in the perceptron we have discontinuous threshold, right? The threshold is not so continuous. Sometimes we have higher threshold, sometimes we have lower threshold. It cannot be clearly differentiated. But here, in this case, in the sigmoid, we have very smooth and differentiable thresholds, right? We can say on a fixed interval. So that becomes that makes our task easier. So it can you can say that it's a combination of a perceptron, simple perceptron, with the added smoothness and differentiable thresholds. So, and the remaining everything else remains the same, right? We have input from x1 so on till xn, and then we have associated weights w1, w2, and so on wn, right? And then we have the summation, the sigmoid function here. And as you can see from the diagram here, that the axis, if you carefully notice, that it starts from the zero and it goes on reaches to 1, right? So the function lies between 0 to 1. There is no negative, right? For example, uh, it is not starting like this and going like this, right? So if in that case, that will be like -1 to -1 to +1, right? So which is not the case here. This is not the case. Uh, Here the case is, if we have this axis, you can clearly see that it starts from the 0 and it goes to +1, right? So this is 0, it goes to +1. So the function or the value of this output will definitely lie between 0 and 1. Now how that function, how these formulas, what are these they mean, we will slowly understand each and every aspect of it. Right. So, like I mentioned, it is almost like a perceptron, but the sigmoid unit first computes the linear combination of its input, then applies the threshold to the result. Right. So, first is it computes the linear combination, exactly like how we have done in the linear unit. Right. We get the linear output for a linear combination of its input. Right. But here, along with this, we are there also going to apply the threshold to the result. Right. Please remember this point. We are applying threshold to the result. Now the threshold output that we get is a continuous function of its input, which we were actually looking for, right? We were looking for a continuous function. Whereas in the previous case, that is perceptron unit, we had discontinuous function, discontinuous threshold, which was not acceptable, right? So we have the threshold output, which is a continuous function of its input, and more precisely the sigmoid unit, right, computes the output as given by this function. So O, which is the output, is equal to the sigmoid function of the product of weight vector as well as the input vector, right? So this symbol represents the sigmoid function here, right? Or sigmoid function, or in other words, it is also known as logistic function, right? So what is this sigmoid, right? What is this sigmoid? How do we define the sigmoid? So sigmoid is constant again, right, which is given by this formula. So sigmoid of, let's say, a variable y, it can be any variable, it can be x, y, a, b, c, whatever the variable is. So sigmoid of that particular variable is equal to the ratio divided by 1 to 1 plus e raised to minus y, whatever that variable is. So y is the variable here. So it is the inverse exponential, you can see. So the important aspect here to be noticed is the output ranges. Again, I have to mention here that the output ranges between 0 and 1, and increasingly monotonically with its input, right? And increasing monotonically with its input. So which you must have observed here in the figure 4.6 here, right? So this is what I am talking about. Right. So the output ranges from 0 to +1. Right. So hope you understand what is basically a multi-layer network and how it gives us better result compared to a perceptron rule or a linear unit or a perceptron unit for that matter, and when to prefer it. Right. So Yeah, this is the multi-layered network diagram, and this is the decision surface. And as you can clearly see, it is somewhat successful in uh, drawing a region or differentiating the training examples with the identical, set of training examples, which in this case was the speech recognition in the context of the vowels, right? Right. So with this understanding in the background of our multi-layered network, we shall discuss the back propagation. But let me take the doubts. If you have any doubts, you can ask. Anybody with any doubt? Please respond, guys. Anybody any doubt? Yeah. If you have any doubts, please ask. Anybody with any doubt, please respond. Okay. Fine. So, since we have discussed about the aspects of these multi-layered network and we are now ready for understanding the backpropagation algorithm, so we will take up this backpropagation algorithm. But since we have this backpropagation algorithm for our lab experiment, machine learning lab as well, so I shall discuss this backpropagation algorithm in the lab session, which will be maybe we will have it tomorrow or day after tomorrow. So we will have a proper session in which we will discuss the complete algorithm of this backpropagation, how it can be implemented, and we will also execute and see how backpropagation algorithm would look like, right? So that session will cover our fourth experiment of our machine learning, that is the backpropagation algorithm. So I was waiting for these theoretical aspects of the understanding that we require to understand this backpropagation algorithm to get finished, right? So now since we have discussed all the important aspect of how backpropagation algorithm can be used, and we are ready with the theory of it. So in the next session, we'll be discussing practically. We will first see the algorithm of the backpropagation algorithm. Then we will understand each step by step how it can be implemented. We will take some input data, we will execute them. We will also observe how we get the output, right? So we will have that application algorithm session maybe tomorrow or day after tomorrow, right? So meantime, please go through these theoretical aspects of this application algorithm again, and as you must have been already preparing the notes, start preparing the notes, which will be your assignment itself, right? So your assignment 2 will be whatever we have covered after your first eye, handwritten notes of whatever we have discussed here, right? Those lectures till we have the dates for the second eye. So whatever we cover in this in between, that everything we have to produce in the form of handwritten notes. That itself will be your assignment, right? So apart from that, the lab experiments and those things. I believe experiment number 1, 2, and 3 you already have completed. Few of them have already submitted it. Uh, Few of them have still not submitted the lab journals. That is for experiment number 1, 2, and 3. Right. So those who have not done it, please make sure that you do it as soon as possible because you have marks for it. Right? So if you don't submit on time, you will be losing some marks from the lab experimentals. It is everything is digitalized, so whoever submits on time, who is submitting not on time, everything has a record. So if you are submitting late, of course, marks will be reduced. Right. depending on the how much late you make. Fine. So with this, we will conclude today's lecture, and we will meet in the next lecture with discussing the back propagation algorithm and executing the back propagation algorithm. So you can leave the lecture. Thank you.